Hello and welcome to this lesson on standard form. My name is Edgar Van Hook. I'm the Director of Science at Midhurst Royal College and I'm one of the physics teachers there. In this lesson we're going to look at how to read, write and use standard form numbers for Key Stage 5 Science. To get started with standard form, the basic knowledge you need is very limited. All we really need to know is that 100 can be represented as 10 squared and 1000 as 10 cubed. And that 1 divided by 10 will be 0.1 and 1 divided by 100 will be 0.01. Everything else we will build off that basic knowledge. So what is standard form, and even why bother using standard form? First of all, standard form is a very handy way, very convenient way to express very large or very small numbers. If I wanted to tell you the size of an atom in meters, I would say 0.0000000. I would need to repeat 0 15 times before I got to the 1 meters. If I'm talking about that in standard form, I can say it is 1 times 10 to the minus 15 meters. A more familiar number perhaps for us is the speed of light. The speed of light, and I've got a non-rounded version there, or less rounded version there, is 299,800,000 meters per second, but we can represent that in standard form as 2.998 times 10 to the power of 8 meters per second. So this is a standard way where actually we don't have lots of leading or trailing zeros. It's a standard way of expressing very large and very small numbers. So a standard form number is actually the product of two numbers. The first part of it is called the digit number. In the example above, that's 2.998. That is always a number between 0 and 9.99 or so. The second part of a standard form number is called the exponential number, which in this example is 10 to the power of 8. So this is a number where we have 10 raised to a certain power. And at the beginning I said that our basic knowledge we need to know is things like 10 squared or 10 cubed. 10 squared means 10 raised to the power of 2, which we know is 100, and 10 cubed is 10 raised to the power of 3, which we know is 1000. So numbers in standard form, they are generally written there as a multiplied by 10 to the power of n, where a is going to be anything between 1 and 10 or 9.999. N can take any value at all, so long as it is an integer value. So let's have a look in a little bit more detail about how standard form works, taking a few numbers here as our examples. So first of all, what I'm going to do is I'm going to write each of these out, or the first couple out, in terms of their digit number and their exponential number. So 54,000 here, we can represent that as 5.4 multiplied by 10 to the power of 4. I'll do the next two as well. I'll just write those bits out first. 3,210 can be represented as 3.12 multiplied by 10 to the power of 3. And 523 can be written as 5.23 multiplied by 10 to the power of 2. I think it's useful just to go over exactly what do we mean by this 10 to the power of 4. What we mean by that is we are doing 10 multiplied by itself 4 times. So 10 times 10 times 10 times 10, we know gives us 10 to the power of 4. Actually, it's helpful to work our way up from here. We know 10 squared is 10 times 10, and that gives us 100. And so if we do 5.23 multiplied by 100, we get 523. Likewise, for 1000, we can do 10 times 10 times 10. It's 10 lots of 100. That gives us 1000. So 1000 multiplied by 3.21 gives us 3021. And so our 10,000 up here 10 to the 4 means 10,000, so we're doing 5.4 multiplied by 10,000, and that gives us 54,000. Let's now keep working our way down here, and we continue to follow this pattern. So here we're going to have 10 to the power of 1. And hopefully what you can see here, by the way, I've arranged these quite neatly in terms of having the units column, the tens column, and the hundreds column, which you'll be used to from way back when you first started learning about these sort of things in primary school. So here at 19.6, we are doing 1.96, and we're multiplying that by 10 to the power of 1, which is simply 10. Okay, that's just 10 not multiplied by anything. The next one down, we've got here 1.25, and what this is, we're multiplying here by 10 to the power of 0. And what is 10 to the power of 0? Well, all of these I've really missed something out, and what I really should be writing here is I should be writing 1 times 10. This should be 1 times 10 times 10, and here 1 times 10 times 10 times 10. So here this is going to be 1 not multiplied by 10. I don't put multiplied by 0, I just put 1 on its own. So here what I'm doing is I'm doing 1.25 multiplied by 1, and that obviously gives me 1.25. Now, as we then start to go into smaller numbers, our pattern changes ever so slightly. Here we've got 1.79, and this is going to now be multiplied by, what we do here is we do 10 to the power of, well, we've done 4, 3, 2, 1, 0. The next logical one down is minus 1. Now what we were doing with all of these, I've been saying this should be 1 times, well, 10 times 10 times 10, 10 times 10 times 10, 10 times 10, 10, not multiplying by 10. What I do here is I now start to do the opposite of multiplying. So in each case I'm multiplying by 10 even less. Here I'm not doing any multiplying by 10. So if I'm going to do something less than multiplying, the opposite to multiplying becomes division. So I don't do multiplied by, instead I do divided by, 1 divided by 10, which we know gives us 0.1. So what I'm going to do here is I do 1.79, and then I'm going to multiply that by 0.1. Multiply that by 0.1, and my answer will be 0.179. Just gone off the screen there, sorry. So we can keep on with that pattern. Here we've got 5.80. I must keep that trailing 0 here. That is then going to be multiplied by, hopefully you've guessed it, that's right, 10 to the minus 2. And what I do in this particular case, it's going to be 1 divided by 10 times 10, which gives us 0.01. So here, what I've got is I've got 5.80. That is then multiplied by 0.01, and that gives me an answer of 0.0580. So for the last one here, hopefully the pattern is now becoming well established for you. We're doing 9.67. We're multiplying that here by 10 to the minus 3, and we understand that to be 1 divided by 10 times 10 times 10, which gives us 0.001, and so we can then write that there as 9.67 multiplied by 0.001, and that gives us an answer of 0.00967. So let's now take a look at how we use standard form on a calculator, how a calculator can be used to perform standard form calculations. Let's start with our example number here, 7.5 times 10 to the power of 6. The first thing that we do is we input the digit number, 7.5. Then what we need to do is we need to use this button here, times 10 to the power of x. It may be on your calculator as an EXP. You will need a scientific calculator to do these calculations, and I do recommend you have a scientific calculator rather than just using your phone or a more basic calculator. So here we go, times 10 to the power of, and we then put in 6. What the calculator does is it interprets the 7.5, the digit number, and the 6, the exponent number, as a single number because we've got this times 10 to the power of x button. If we use a multiplied by symbol, and then we do shift and 10 to the power of whatever up here, it doesn't necessarily interpret it as a single number. So this is a very, very useful button because essentially what it does is the calculator automatically puts brackets around it, which is then useful once we then start doing further operations with it. So we do that. If I press equals now, I get 7.5 million. Very straightforward like that. So let's have a look at an example calculation. I'm going to multiply 8.3, press this button here to the 5, and if I can then go straight into multiplication because the calculator has already interpreted the 8.3 times 10 to the 5 as a single number. The calculator has already put brackets around the 8.3 times 10 to the 5 because I've used this. This button holds those two together. So we then do that as 1.6 times 10 to the power of 6, and we get an answer of 1.328 times 10 to the power of 12. So here's an example calculation I'd like you to have a go at doing. When it comes to doing the minus for the times 10 to the power of minus 7, don't use a negative here because that's an operation that's telling the calculator to take one number away from the other. Rather use this button up here, the minus with brackets around it, as that indicates that whatever number it's placed in front of is a negative number. So you could do, if you do negative 7, that says it's minus 7. Give that a go, pause the video and give that a go. So hopefully the answer that you will have, you've got 7.2 times 10 to the 14 divided by 3.6 times 10 to the minus 7 using this negative 7 button there, and we should have 2 times 10 to the power of 21. So here is an example I would like you to have a go at, just to check that you're getting these ideas. So first of all, in that first statement there, we've got a number written in standard form, and I'd like you to write that in decimal form in our more usual numbers. And then secondly, the second part of this is going to involve a calculation, and I'd like you to have a go at doing that. Pause the video, and when you are ready, you can restart. So the answer to the first part, we should have a number with 4, then 7 followed by 11 zeros. Essentially we've got the 4 followed by 12 further placeholders. And as you can see here, I've separated those up into groups of 3, as is the sort of standard normal way of doing this, which helps to actually read those numbers accurately. The second part of this, we've got 4.7 times 10 to the power of 7 divided by 5.88 times 10 to the power of 8, and that should give us an answer of around about 8 times 10 to the power of 3, which of course we can interpret as 8,000 times farther. So now we're going to look at how we can use standard form to effectively deal with prefixes in numbers that we may be given. So we've got two numbers here, one of which is in normal decimal form, one of which is in standard form, and we're going to have a go at removing their prefixes. So let's start with that first one, 650 nanometers. We should know that a nanometer, that prefix nano, lowercase n, represents 10 to the power of minus 9. So we can rewrite that as 650 times 10 to the power of minus 9 meters. We substitute the 10 to the power of minus 9 in place of the lowercase n. That we can then work out. You could enter that into your calculator and it will give you a value of 6.5 times 10 to the minus 7 meters. So that's a way of removing the nano there when you don't have a standard form number. Our second example, we've got 1.3 times 10 to the power of 8 kilometers. We know that the kilo, lowercase k, represents 10 to the power of 3. So we can rewrite that as 1.3 times 10 to the power of 8 times 10 to the power of 3 meters. Then using our rules of indices, we know that 10 to the power of 8 multiplied by 10 to the power of 3 is 10 to the power of 8 plus 3, which will be 11. So we have 1.3 times 10 to the power of 11 meters. Now it's your turn. I'd like you to have a go to rewrite these values, removing their prefixes. Pause the video, and when you are ready, restart the video. So the first example there, 0.5 micrometers. The micro symbol, the mu symbol, represents 10 to the power of minus 6. So we can write 0.5 times 10 to the power of minus 6 meters. If you enter that in your calculator, you will get 5 times 10 to the power of minus 7 meters. Our second example there, we've got 6.50 times 10 to the power of 4 mega newtons, capital M newtons. The capital M represents times 10 to the power of 6. So we can rewrite that as 6.5 times 10 to the power of 4 times 10 to the power of 6. When we've got 10 to the power of 4 multiplied by 10 to the power of 6, we use our indices rule. So that will be 10 to the power of 4 plus 6, which will be 10 to the power of 10 newtons. We must, in this particular case, keep that trailing 0 in the 6.50, as that implies a certain level of precision to the measurement that we've got there that we need to maintain.